being a chemist, the title of my presentation is the designing of nanocatalysts for hydrogen energy generation and the heterogeneous organic transformation reaction, which is the best fit for the theme of this catalysis, chemical engineering, and the technology conference, because the core theme of this conference is the nanocatalysis, and my area is a perfect match of this event for today's presentation. So actually, when we talk about, actually, I will speak over the nanocatalyst, means designing of the nanomaterials as catalyst for hydrogen energy generation and the organic transformation reaction. So briefly, I will speak over the uh, nanomaterials. Actually, when we talk about the nanomaterials or the nanostructure, then the first point that came in our mind, this is the uh, that nano is one of the dimension of the length, right? So we can correlate the 1 meter dimension with the general dimension of the length with other dimensions like the inches, centimeter, millimeter, micrometer, or the nanometer. For example, 1 meter is equivalent to the 1 million micrometer, or in other words, 1 micrometer could be defined as 1 millionth part of the meter. Now, 1 meter is equivalent to the 1 billion nanometer, or 1 nanometer length is equivalent to 1 billionth part of the meter. So as a number, this is 1 billion. So, for example, if I am having a rod of 1 meter length, and if I cut this rod into the 1 billion pieces, then the length of one piece is 1 nanometer, and this dimension is the smaller than the wavelength of the light. So, actually, the nanomaterials are very fine materials whose grain size lies in the range of 1 to 100 nanometers, and because of the different dimensions, the nanomaterials or nanostructures could be classified in different classes like nanomaterials, nanoparticles, nanorods, nanowires, tubes, nanocylinders, bipods, tripods, tetrapods, composites, portion nanostructures, depending on their actually structures. Like this is the bipod, tripod, tetrapod structure. These are the nanowires. These are the nanotubes, and this is the portion nanostructure. So, for example, if we are having the portion nanostructure, then either the core or the shell thickness should be in the nano region. Then we can call this structure as the portion nanostructure. So, at this the material at this very fine dimension could exhibit the unusual properties because of the confinement of electrons. They will have the high surface area, and because of their small size, there are large number of electric and magnetic dipoles at the surface, and of course they will be highly disordered. So because of these unusual reasons, these materials could be used in electronic devices, memory devices, catalysis, sensors, and energy. And for these three parts, I will speak here briefly in my presentation. So actually, if you could see actually different objects that are present in nature, then you could classify these objects on the basis of their dimension. For example, if you move from a few centimeters to the few nanometers, then the nature of the object may change from football to fluorine. Meanwhile, you could see the different objects of different sizes, like the human hair of size few micrometers, red blood cells of size 100 or 100 to 200 nanometers, and the virus of size around 50 nanometers. So actually, what happens when we actually reduce the size of the objects from bigger size to the smaller size, then the number of atoms at the surface, they will increase, and the surface energy is associated with these number of atoms. And since the number of atoms are increasing drastically when we reduce the size, then the surface energy will increase, and the surface energy is proportional to the surface area. Therefore, the surface area for a constant volume will increase drastically when we reduce the size of the object to nanometric or the small dimension. So this is the mathematical concept, how the surface area actually increases when we reduce the size of the objects. So this is the example. Like for example, if you have a one cube, bigger cube, its covered surface area is 6 square centimeter, and if you broken down this cube into 8 smaller cubes or the 60 smaller cubes, the covered surface area will increase to 12 and then 24 square centimeter. And what is the mathematical calculation? How to calculate the surface area? So this is the mathematical calculation. For example, you have a one cube of dimension 2 centimeter length. So how would you calculate the covered surface area? Then actually a cube having 6 surfaces and each surface is a square, and the area of a square is the length into width. So the area of square or one surface will be 2 into 2. And how many surfaces we are having in a cube? There are 6 surfaces. So we have to multiply this 2 into 2 with 6. So the total area will be 24 square centimeter. Now I am actually cutting down this 2 centimeter cube into 1 centimeter cube. So how many cubes actually it will generate? It will generate how many cubes? 1, 2, 3, 4, 4 this side and 4 back side. So 8 cubes it will generate. And now you can calculate the covered surface area of these 8 cubes. It will be 8 into 6. 6 means number of surfaces. 8 is number of cubes. 6 is number of surfaces. 1 into 1 is the area of a square. So this will be 48 square centimeter. So just by reducing the size of the cube from 2 centimeter length to the 1 centimeter length, its covered area will increase from 24 square centimeter to 48 square centimeter. So now when we reduce the size of the objects from micrometer to the nanometers, means 1000 times reduction in the size. Now you can actually think over it, how much times surface area will increase. And surface area is a very important property when you work over in nanocatalysis, photocatalysis, electrocatalysis, or the organocatalysis. So actually when the particle size become very small, so most of the physical and the chemical laws differs, and because of the variation in the difference in the physical and the chemical laws, the associated properties like electronic, physical and the chemical properties actually changes. For example, the quantum size effect, optical band gap will change actually when we bring down the size into the nano dimension. The melting point will change. Reactivity, catalysis, structure. I will speak over the catalysis part. For example, melting point. Actually, the reported melting point of bulk gold is around 1000 degrees centigrade. But when you have the fine nanoparticles of gold, means 2.5 nanometer, then it will have a small crystal lattice. So its melting point will reduce to 300 degrees centigrade. So this is the example of the catalysis. Means if you have the bulk gold oxide surface, then it won't have the oxidation of carbon monoxide. But if you have the nano-sized gold oxide surface, then it helps the oxidation from carbon monoxide to the carbon dioxide. So actually in this slide I am showing that the nanoscience or nanotechnology is called as highly interdisciplinary or the multidisciplinary field. Why? Because actually the nanomaterials exhibit the different properties or enhanced properties like the high conductivity, high strength, high reactivity. Their durability and resistance is very high for the towards degradation, and because of their small size, they could be easily transported in a variety of the matrices. So either the researchers, either they belong to the material science, metallurgy, mechanical engineering, life science, electrical engineering, computer science, chemistry, biology, physics. They could have actually the single platform of discussion or to exchange their ideas, that is called as the nanoscience or the nanotechnology. So therefore, nano is considered as highly interdisciplinary or the multidisciplinary field. What are the actually stems of nano? Is nano new? So my answer is nano is not new actually. You could see this is the cup. It was placed in British Museum, London, for 4th century AD. And this cup was actually appear as red or green in color when it is in different types of light. But at that time it was actually considered as miracle. But nowadays actually it has been established that the gold particles exhibit the different color when they are in the different sizes. So gold actually particles make building blocks from atomic to microscopic sizes, and by changing their color. So this nanotechnology has its roots by the very famous lecture. There's a plenty of room at the bottom. It was delivered by physicist Nobel laureate Professor Richard Feynman. He was very clear at that time that time will come when the scientists or the researchers or the young students will think over the manipulation of the small objects or the small materials to increase their properties. And nowadays, actually, we are doing the same thing. So actually in this slide, actually very basic slide actually, which shows what is the meaning of the nanoscience or the nanotechnology. Basically, nanoscience deals with the fabrication of the materials, characterization or the proper measurement of the properties of the nanomaterials, which is significantly different from the bulk materials. Whereas the nanotechnology deals with the production or application of the nanomaterials for their in terms of devices and systems by controlling their shape and size at nanometric scale. So basically, nanotechnology uses science at the nano scale. So since actually I am speaking over this. Nanocatalysis. So actually, there are various forms of the nanocatalysis. One form is the heterogeneous nanocatalysis, where actually we take the opportunity to work over the organic catalysis. In the organocatalysis, actually, there are millions of the organic transformations that are known, which are supported by the inorganic catalyst. So nowadays, actually, what we are doing that we are actually transforming the inorganic catalyst into inorganic nanocatalyst. So actually, we are able to transform those millions of organic transformation uh, uh, into the organic with the help of the inorganic nanocatalyst. So this area is called as the heterogeneous nanocatalyst. So the other area is the other part of the nanocatalysis, the photocatalysis, where or electrocatalysis or photoelectrocatalysis. So with the help of these three processes, we could actually split water into the hydrogen gas, and by means of the different actually instrumentation or the different actually strategies. So here today I will speak over all these parts very briefly. So by using these three methodology, we are able to obtain the hydrogen, or we could produce hydrogen with the help of the water splitting reactions, with the help of our designed nanocatalyst. So and actually the basic theme actually to design these nanocatalysts, that we should have the their optical band gap in the visible light. Means visible light driven nanocatalysts we could actually fabricate. Why? Because actually, if you could see the spectrum of the solar energy of sun, then it has nearly 46% of the visible light, and the visible light, the wavelength of the visible light is around 400 to 700 nanometer. So the optical band gap is from 1.8 electron volt to 3.2 electron volt. So actually, if we are able to split water with the help of the visible light, means the nanocatalyst having the optical band gap in the visible region, then this method is highly feasible, or it is the cost effective. So generally, the optical band gap tuning we generally do either by chemical modification or to design the hetero structures, so that actually we can tune their optical band gap by reducing the grain size or increasing the surface area. And by this way, actually, we are able to design the visible light active photocatalyst to increase their photocatalytic efficiency. So this is the actually the main objective, or the think tank behind this problem. So yeah. So now photocatalytic water splitting application. So this is the actually setup that we are having in my research lab here in New Delhi, Jamia. So here actually we prepare the aqueous media by taking the water, our nanocatalyst means nanomaterials, and the appropriate amount of the sacrificial agents. So for different reaction setups, we could actually able to have the different sacrificial agents. So this is the UV or the visible light source. So if we apply visible light, and this light is able to actually uh, evolve electrons in the conduction band and holes in the valence band, and these electrons could be transferred into the aqueous solution, where it can reduce the H plus into the hydrogen gas. So if we can liberate hydrogen, then actually we can allow this liberated hydrogen into the GC uh, machine supported by the PCB detector, and if hydrogen is there, then the very clear signal could be actually appeared over the screen, and the sacrificial agent could lose their identity to occupy the Foley structure. This is the proposed mechanism how we would get the hydrogen evaluation using photocatalysis. And there are certain applications of our actually materials, actually our nanomaterials or these advanced materials could have applications in the energy production, environmental radiation, cosmetics, sensors, and photovoltaic applications. So generally, we have two methodologies for the fabrication of the nanomaterials. One is the top-down approach. Actually, where we have the bigger size particles and we broken down into the smaller size particles by applying some physical forces. So these methods are called as physical methods, and generally the people which are actually belongs to the physics or mechanical background, generally they use this method like high energy bar milling, inert gas condensation, spray pyrolysis, electrodeposition, plasma synthesis, R discharge method, and laser ablation method. The second actually approach is the bottom up approach. In the bottom up approach, where we have the atomic size particles, we could actually condense by chemical means into the nano size particles. So actually we have a number of chemical methods like the chemical, solvothermal, hydrothermal, polymeric state precursor, or the sol gel method, or the reverse microemulsion method. So actually to make the nanomaterials. So these methods are called as the chemical methods. So being chemist, we use all these chemical methods. I am very fortunate that I am able to having the set up all kind of the chemical methods in my research lab. So this is the hydrothermal synthesis assembly where we have the hydrothermal autoclave or the hydrothermal bomb, and it has a Teflon liner actually, which actually helps to prevent the corrosion with the stainless steel surface. And here you could take the reaction mixture, place this reaction mixture over by actually fixing the stainless steel airtight lid in the vacuum oven, and these are the actually the reaction steps by how much amount of the starting reagent you could take, and what are the actually steps. Actually, we have reported all kind of steps in our different papers. So finally, you are able to prepare the nanomaterials by using this method. So uh, so we have actually just recently this paper was published. We have prepared the silver doped SNO2 nanostructures using the hydrothermal assembly, and we have applied this material for the photocatalytic water splitting and the nitrophenol detection. So this is the X-ray diffraction pattern, which shows that each diffraction peak could be indexed into the silver doped SNO2 nanoparticles, and no additional peak or the slight shifting of the diffraction pattern confirms the successful doping of silver over the SNO2 post lattice. And here, this is the UV visible plot which gives the optical band gap of silver doped SNO2 nanoparticles. These are the SEM and the index spectra, which show that the particles are uniformly distributed, though they will have the roughness and densification could be seen, and which is actually expected because actually silver nanoparticles having high surface energy, and so they could actually able to produce particles with high density, and this is the elemental mapping as well as the EX spectra, which shows that the experimentally derived chemical composition was found to have very close agreement with the theoretically loaded composition, and this study is associated to the incorporation of the metal over the host lattice. So these are the detailed HRTM, selected area electron diffraction, high resolution transmission electron microscopic studies, which shows that the actually lattice fringes are clearly indexed with the lattice planes as reported in the X-ray diffraction pattern. And here the distinct circular rings in selected area electron diffraction, also indexed with the X-ray diffraction pattern. And very high surface area we have obtained by using the DET surface area studies, and we put it for the first time for silver doped SNO2 nanoparticles. Then actually we do the photocatalytic water splitting measurements for the hydrogen energy generation, and we are able to obtain very a high amount of the hydrogen energy, which is 19.4 millimole per gram catalyst in 8 hours. This amount was high as compared to 2.5 and 5% silver doped nanoparticle. Actually, high doping of the silver doping provide actually producing the corrosive effect for the hydrogen generation. We also do the cyclability or the cycling test, which shows the consistent performance over 3 consecutive cycles. We are able to obtain the stable rate of hydrogen production with the help of the silver doped SNO2 nanoparticles. And we found that the 1% silver doping providing the synergistic effect as compared to 2.5 and 5% silver doping over SNO2 particles. So then we have applied these S-bit silver doped SNO2 nanoparticles over catalytic transformation from 4-nitrophenol to 4-aminophenol, and we observed this transformation with the help of the visible studies, and we found that the absorption band of 4-nitrophenol start decreasing as the time of the reaction increasing, and the intermediate peak of 4-nitrophenolate ion will increase, and finally as the reaction goes for completion, the corresponding absorption peak of 4-aminophenol is actually start observing. So these are the actually kinetic plots of this conversion reaction. Means the nearly 100% conversion of nitrophenol to aminophenol where is done in 5 minutes. Then you have 5% silver doped SNO2 nanoparticle, whereas 1 or 2.5% provides this conversion in 30 or 22 minutes. And this is a cyclability test that we do for the 5% silver doped SNO2 nanoparticle as nanocatalyst for after getting recovery after at the end of the reaction. And this is the detailed mechanism which shows that the silver doped SNO2 nanoparticle act as catalyst with the sodium borohydride as reducing agent. Then these electrons which are produced by the catalyst as well as the hydrogen, reducing hydrogen can reduce the 4-nitrophenol over 4-aminophenol via 4-nitrophenolate. So this is the possible mechanism that we have reported in the literature. Then we have actually prepared the chromium doped SNO2 nanostructures by modified solvothermal method for the enhanced photocatalytic and electrochemical water splitting applications. So here this is the X-ray diffraction pattern, and which shows the confirmed chromium doping of over the SNO2 nanostructures by type 16 of the diffraction pattern is obtained by the variation in relative parameters, and these are the optical band gap studies. So these are the basic characterization using the TEM, SEM, selected area electron diffraction, and energy dispersive analysis of X-ray studies, which shows the nanophase formation of chromium doped SNO2 nanoparticles, and the EDEX studies shows that the experimentally loaded composition could have the close agreement with the theoretically loaded composition for the chromium doped SNO2 nanoparticles. So this is the photocatalytic water splitting studies. This is the photocatalytic water splitting studies. It shows that the 5% chromium doped SNO2 nanoparticles give the maximum yield of hydrogen, which is 11.74 millimole per hour per gram of the catalyst, and which was found to be quite high as compared to the 2.5 and 1% SNO2. So these are the pictorial representation of each composition, and shows the comparative study of the hydrogen evaluation for different materials, and this is the average hydrogen evaluation per hour with the standard deviation, and this gives the cyclability test recycling, and we tested for the cyclability test for the stability and reusability for the rate of hydrogen production for 3 consecutive cycles, and we obtained the high stability chromium doped SNO2 nanoparticles. And these are the electrocatalytic water splitting studies. Here we do the oxygen evaluation and hydrogen evaluation reaction with the help of the CV, LSV, CA, and the Tefel slopes, and the low value of the Tefel slopes shows that the significant hydrogen production in the electrocatalytic studies of chromium doped SNO2 nanoparticles. And this is strontium doped SNO2 nanoparticles, and these are the basic characterization of XRD, UV, PET surface area, and all the basic characterization shows that this was actually we are able to obtain the monophasic strontium doped SNO2 nanoparticles. Very beautiful TEM, selected area electron diffraction, HRTM image could be seen over here, and each lattice fringe, the width of the lattice fringe and the circular diameter of the circular range could be indexed with the X-ray diffraction pattern as we observed during the synthesis. This is the SEM and the index pattern, which gives a very satisfactory result for our as compared strontium doped SNO2 nanoparticles. And these are the hydrogen evaluation study, and we obtained a very high value of hydrogen generation, which was around 37.3 millimole per hour per liter for 5% strontium doped SNO2 nanoparticles, and which was nearly 1.17 or 1.78 times higher than that of 2.5 or 1% strontium doped SNO2 nanoparticles. And just 1 hour before, I got the acceptance of this study in nanotechnology. So we just got the acceptance. So I have just corrected over here. So the photocatalytic hydrogen evaluation performance we obtained for maximum for 5%, then 2.5, and then 1%. Then this is the polymeric citrate precursor method. The polymeric citrate precursor method, actually the backbone of this method is the esterification reaction between ethylene glycol and citric acid. It forms 5 to 6 membered ring of metal citrate complex, which is known as the polymeric matrix or the cavity, which acts as the nanoreactor. This method, actually, this polymeric citrate precursor method is very simple method because actually it doesn't require expensive chemicals, glass layers, or the equipment. This method is not sensitive to the presence of water. It does not require any inert atmosphere even without careful control of gel processing time and condition. High degree of homogenization is obtained. And this is the schematic of the or the flow diagram for the reaction steps, how to get the various nanostructure by using polymeric citrate precursor method. So by using this method, we have prepared yttrium ferrite nanoparticles. So this is the X-ray diffraction, TEM, and the selected area electron diffraction pattern, which shows that the YFO3 was indexed in the orthorhombic structure with an average grain size of 77 nanometer. So this is the MH plot and this is the P plot, which gives the hysteresis corroborates for the ferromagnetic and the ferroelectric characteristics, which confirm the multiferric characteristics in YFO3 nanoparticles. We have applied this YFO3 for the hydrogen evaluation, and this is the hydrogen evaluation plot, which shows that the maximum hydrogen of around 131.6 micromole per hour per gram were obtained using YFUC nanoparticle, and the linear relation of hydrogen evaluation with time then correlate this significant photocatalysis using YFUC nanoparticle under visible light irradiation. We have also actually fabricated the dye-synthesized solar cells with the help of YFUC nanoparticles for the energy conversion devices, and we have shown that the power conversion efficiency of YFUC TiO2 based system could enhance nearly 5 times as compared to TiO2 based DHFC after adding the nanocrystalline YFUC nanoparticle. And this is copper chromate nanoparticle. We also prepared using polymeric precursor method. Very beautiful X-ray diffraction TN picture. You could see over here, and we actually, with the help of this material we are able to reduce nearly 80% of the methylene dye. So there's nothing important actually in this study. So I'm coming to the next. This is the sodium niobate nanoparticle that we have actually prepared the polymeric precursor method. And here you could see the X-ray diffraction pattern of nanocrystalline phase and the bulk phase, actually to compare with the studies. And these are the TM image which gives the average size of 15 nanometer, and HR image gives the latest range of length 0.178 nanometer, which corresponds to 141 crystal grain of NaNO3. And these are the detailed electrolysis, electrocatalytic studies of sodium niobate for oxygen evaluation reaction and the hydrogen evaluation reaction. And the detailed studies show that the low value of the Keppel slope and the high value of the current density for both hydrogen evaluation and the oxygen evaluation reaction for the nano size NaNO3 as compared to bulk NaNO3 nanoparticle. NaNO3 show the significant electrocatalysis by using NaNO3. We also do the dye degradation of both Bengal dye using sodium niobate nanoparticle, and we are able to degrade nearly 86% dye without exposure. And the possible degradation pathways to establish using these LC-MS studies for our material. And this is sodium tetrate nanoparticles. We have prepared using polymeric precursor method. You could see very beautiful X-ray diffraction pattern which was indexed in the orthorhombic structure, and this is the TM image which gives the average grain size of the 70 nanometer, and this is the size histogram, and these are the detailed SEM micrograph for sodium pentylate nanoparticles at different sintering temperature or the annealing temperature like 500, 600, and 700 degrees centigrade. These are the photocatalytic studies. We do actually the degradation of the methylene blue dye into mediums, neutral and the alkaline medium, and we found that nearly 96% dye was degraded to 100 minutes when the medium was neutral. But when we change the medium from neutral to alkaline, then the same amount of the dye was degraded in 80 minutes. So this was a significant result that we obtained for methylene blue dye. And with the help of the LCMS study, the possible degradation pathway of the methylene blue they have reported in literature. And this is the ruthenium oxide nanoparticle for sensing purpose as well as for hydrogen generation. And this we have prepared using the wet chemical synthesis method, and a very beautiful actually image is shown over here. And this is the sensing property which shows that the maximum activity of ruthenium oxide nanoparticle, could be observed at high concentration of H2O2 and as compared to HRP enzyme. And on further actually increasing the concentration of H2O2, the catalytic activity was suppressed. And this is thermal stability plot which shows that the catalytic activity of ruthenium oxide nanoparticles was almost preserved till 90 minutes at 80 degrees centigrade, whereas the HRP enzyme showed no activity at all. And these are the electrocatalytic CV plots, CV, LSV plots for ruthenium oxide. It showed that the more current could generate in air as compared to nitrogen as well as oxygen saturated atmosphere for the oxygen devaluation reaction. So these measurements actually could be useful for giving the information about the onset potential, reaction kinetics, mechanism of the reaction, as well as to identify the number of electrons involved in the electrochemical reaction. The water splitting reaction means for hydrogen generation could also be commented with the help of these studies. So there is a chronoamperometric plot which shows that the constant current could be generated with time, which reflects the stability in S prepared material. So these are the Tafel slopes graph in air, nitrogen, and oxygen. In all the graphs, the oxygen reduction reaction means hydrogen evaluation reaction uh, were found to be, the values were found to be low as compared to oxygen evaluation reaction. It shows that the this material could be used for the significant hydrogen evaluation reactions, and with the help of these values, we could optimize this material for the water splitting reaction. And the last material for this today's presentation is the iron oxide actually nanostructures. We have actually prepared these iron oxide nanostructures by using the simple co-precipitation method. Uh, so X-ray diffraction studies shows that it was indexed in the cubic structure, and these are the very beautiful TM picture which gives the cubic structure formation of cubes, and this is the HRTM image which gives the formation of the clear lit fringes, and each circular rings in the selected area electron diffraction pattern could be indexed in iron oxide, and actually the since iron is a transition element, so it could actually exhibit the different oxidation states. So when we actually load reaction for the formation of Fe3O4, sometime Fe2O3 or FeO could obtain. So to arrive, and X-ray diffraction, sometime X-ray diffraction could not give the information whether these minor phases are obtained. So to get whether we could have the monophasic Fe3O4, we do the Raman and the X-ray studies. So both the studies show that the monophasic Fe3O4 nanoparticle was obtained, and these Fe3O4 was having very high surface area, which was 268 meters per gram, and it was higher as compared to the other reports. So this is the image plot which gives the ferromagnetic characteristic in Fe3O4. This is the electrocatalytic activity. This is CV plot which gives the redox behavior between iron 2 plus and iron 3 plus, and oxygen evaluation reaction could obtain at the node, whereas the hydrogen evaluation reaction was observed at that node. And the LSP plot actually could be used for the water splitting reactions, and this is chronoamperometric plot which was used for the stability and activity of iron oxide nanoparticle. It shows that the electrochemical water splitting reaction stops when current drastically comes to zero, when we switch off the potential, and the low value of the Tafel slope could corresponds to the effectiveness for the hydrogen evaluation reaction for the electroactive catalyst for iron oxide. We have also actually applied this material for the supercapacitive behavior of magnetic iron oxide, and the area under the CV curve shows the efficient supercapacitive behavior of the electrode material, and the nature of the hysteresis, as we see over here, it reveals that S prepared nanomaterials could be used for the energy storage applications, and the stability could be actually achieved by GCD measurements, and show that the good cycling stability with high specific capacitance shows the high supercapacitive performance for magnetically iron oxide. So now to conclude my presentation, the S prepared, we have actually prepared the chromium, strontium, and silver doped SNO2 nanoparticles, and these nanoparticles could be used for photocatalysts, for the photocatalytic water splitting studies for hydrogenation, and the as prepared silver doped SNO2 nanoparticles potentially act as nanocatalysts for organic transformation from 4-nitrophenol to 4-aminophenol. the significant hydrogen evolution and power conversion efficiency using by fusing nanoparticles, and the NaNBO3 and sodium tantalate nanoparticles shows the significant photocatalytic activity towards uh, electrolysis as well as the degradation of the dyes, and the enhanced electrocatalytic and sensing performance was observed and obtained by using ruthenium oxide nanoparticles, and co-precipitation by co-precipitation method iron oxide nanoparticles was obtained, which shows the significant electrochemical water splitting and supercapacitor application. I would like to thank to all my PhD students who have passed and currently working with me in my research lab. And because of their hard work, I am able to present such kind of work. And I also thank my collaborators, Professor Chari from the One University, New Jersey, Professor Banerjee, Texas A&M University, Professor Mao, who is head of chemistry at Chicago, Professor Ahmad in King Saud University, Saudi Arabia. I would also like to thank my funding agencies, actually, who were very kind to support my research lab, DST, SCR, DCSIR, Spark of Government of India, and my university, Jamia Islamia, who gave me the platform to explore my research skills, actually practically on actually bench, and these are the my research citations or the achievements. So I must thank the organizer again for giving me the opportunity to be part of this prestigious conference, and I also thank the audience for the patient listening. Thank you all.